So, Martin, how's about you tell us about the kinematics of giant pulses? You're
really
muted,
understand how I can unmute myself once I'm sharing. So let me try this again. Okay, so I agree that this is really nice. We're doing this, and I would of course want to say that for the person who designed Dragonfly, which is absolutely the most envy-inducing thing I think I've seen in Toronto recently, I'm very flattered that you think what I have to do is envy-inducing. But okay, let's at least all enjoy the cool stuff we're doing, I guess. So yes, I want to talk about something way more detailed and very small scale in a way, which is how one can use scintillation to learn something about giant pulses, and in particular those of the Crab. So I'm probably best start by just telling you what giant pulses are. So the Crab has sort of occasionally sends out these really bright pulses of radio emission, which lasts maybe about a microsecond. And if you study them really carefully, you see here an example on the left. There are usually a couple of such microbursts, and they in turn, if you really zoom in, which I'm not showing here, are made up of so-called nanoshots, which are last about maybe 10 nanoseconds and can have brightness temperatures up to 10 to the 41 Kelvin. So they're incredibly bright, short bursts of emission. A sort of more contemporary relevance is that they may be related to what we're seeing in fast radio bursts, which also are short radio flashes, but then from cosmological distances. And in this graph on the right, there's a sort of a summary of things that can happen at as a function of duration, and then a measure of their brightness. And these fast radio bursts have typical durations of about a millisecond, so that's quite a bit longer. And their luminosities are per second are larger, but it looks in this graph, you already see that some of these giant radio pulses, that is the giant pulses that I will be talking of, have similar brightness temperatures. And in fact, the really short ones are even brighter than the FRBs, though perhaps the FRBs are also made out of smaller pieces, which are super bright. So it's another reason to sort of think, hey, they might be interesting, because in the Crab we can perhaps study them better than these mostly non-repeating things at cosmological distances. Now, what do we know about them? So if I first focus on the left, you have a sort of a pulse profile of the Crab pulsar, and it goes all the way from 330 megahertz, so that's meter wavelength, to sort of high energy X-rays. And these giant pulses, they occur at very particular phases in the Crab pulsar, the main pulse and the interpulse. And these are average pulse profiles, but in reality, you don't always see a pulse in this phase period. You sometimes see a pulse and sometimes not. And then you see that it's completely aligned all the way up to these very high energies, except for a weird region in between, which is certainly not understood. And also in the radio, there's some other emission, like I actually don't know if you can see my cursor, but it's sort of ahead of the main pulse, and that is regular pulsar emission. That is visible every rotation. And because of this alignment, people have thought that that maybe there is a relation between the gamma ray emission and these giant pulses. And the gamma ray emission in neutron stars can only come from fairly far outside, away from the neutron star. So if you have a neutron star here, it looks like a black hole, but imagine a neutron star in there, which is much smaller than that hole. This is an actual numerical simulation of a rapidly rotating neutron star. You have a magnetic field around it, and you sort of see a sort of dipole within the dashed line. And at the dashed line, if you're co-rotating with the neutron star, you're going at the speed of light. So you can't co-rotate anymore, and you get these outgoing pattern of magnetic fields that go in opposite directions. And the idea for the high energy emission is that somewhere where these opposite directions meet, so where you see this extra dense stream of plasma, there's a lot of reconnection there, and that causes both the giant pulses and the high energy emission. And indeed, people have done studies where they looked for these giant pulses and see that at the same time an optical pulse if you stack things where a giant pulse happened versus pulses where it didn't happen, that the optical and X-ray emission is a bit higher. So the idea is that it goes from quite far out. And really what we are thinking of doing, where I've had a sort of general interest in using scintillation as a sort of microscope to look at structures around pulsars and maybe track orbits, is can we somehow tell where the emission really comes from observationally? And to explain why that could work, I should give you another picture, which is, if we start on the right now, these are this is now a single giant pulse observed in multiple different wavelengths. And so at this time scale, it looks like a delta function at 3 gigahertz and 700 megahertz. But as you go to lower and lower frequencies, and therefore longer wavelengths, you see that it doesn't look like a delta function anymore, but it has some kind of exponential decay trailing it. And that is understood. That is because of light taking different paths in the interstellar medium, and in this case actually it's in the nebular medium. So what you should imagine is that the pulsar is somewhere in the middle here. This is the Crab Nebula, and this is sort of an enlarged view around where the pulsar is with its beautiful torus. I'm not going to discuss that any further, but it's too beautiful not to show. But the idea is that this radio emission mostly comes via a straight line towards us, and at high frequencies that is all it does. But that at lower frequencies, the nebular material is able to bend light better and better. The bending angle goes with the wavelength squared, and that therefore more and more paths are possible which arrive with some delay at us. And the delay goes as this bending angle squared over, well, a half bending angle squared and the distance, and then the speed of light to make it a time difference. Now, since this bending angle goes as the wavelength squared, the delay goes as the wavelength to the fourth. And that is why even just going from 200 megahertz to 120 megahertz, you see that this scattering tail becomes a lot longer. Now, how could this help? How could this help us to say something about the Crab pulsar? Is that if you now imagine you have your pulsar exactly here, or very, very close towards it, then the light will follow exactly the same paths, and the pulse would look exactly the same. But if you're a little bit further away, the light will still follow all these different paths, and it will have a similar scattering tail. But in detail, it will not have done the same, and it will lead to a different interference pattern on Earth. And we can estimate what the resolution of this thing is. So basically, the point is you can treat this whole nebula as a whole series of telescopes, all of which are sort of looking at the pulsar from slightly different angles, and we are getting the sum of all their signals with no attempt made to add them really nicely coherently. And so we get some kind of interference pattern between all these signals, and we can ask what the resolution of that is. But before I do that, I did not remember my order quite right. We can just see that this works. So what is shown here is now two spectra of two giant pulses which are very close to each other. This was observed by Jim Cordes et al. And you see that the spectra are quite similar. And that is basically what I was trying to say. If these two pulses are very close to each other, they should follow exactly the same trajectory through the nebula. At least they should, and it turns out later that they don't always. And therefore, they should be very closely correlated. But now if you imagine that pulses are more and more separated in time, then during that time, the pulsar is moving. So at some point, it's going to actually be in a sort of different resolution element, and you should become less and less correlated. And that's exactly what they observe. So for close times, you see it's sort of flat, they're equally correlated. And then as you go to longer and longer times on the right, sort of beyond 20 seconds or so, it's only half as much correlated, and then it goes to zero because your light is following different paths through this nebula, and you get a different interference pattern. Now, one thing I should mention is that this correlation is not exactly 1, but it's rather 1/3, because every one of these giant pulses is made up of multiple components, and that causes its own interference. If you take a spectrum of the whole pulse, and you just inside of that pulse have maybe 10 delta functions, that makes its own interference pattern, and that's different for every pulse. But because you sent it to exactly the same medium, it turns out you can actually derive this quite easily, that then you get a correlation coefficient of 1/3. So that seemed good. And now these pulses, they're all main pulses, and you can sort of say, okay, so clearly we there is some resolution element, and because we know the velocity of the pulsar, we can tell how big that is. It's something like maybe 1,000, 2,000 kilometers. So let me show you how that works then. So I have this particular angle that the light is being bent, and that also means that in the nebula I have effectively some diameter, and so treat this as a maximum bending angle. And so the resolution of my telescope will be lambda over that diameter. And if I multiply that with the distance to the neutron star, I get a sort of spatial resolution at the neutron star. So if you insert for this diameter that it is 2 times this angle times the distance, you get this equation. Insert then a typical scattering time of about a microsecond at 1.5 gigahertz. You find that you get about 500 kilometers resolution. So as this pulsar moves, and it really depends a bit on the numbers, and the pulsar moves about 100 kilometers per second. So from this estimate, you would expect that after about 5 seconds, things start to decohere, but it depends on how much scattering there is, and that varies because this nebula is rather messy, and you look through different parts as the neutron star moves. But anyway, this is quite close to the light cylinder radius of the neutron star. So if something is related to the emission from near the light cylinder, maybe we could tell that things are different. For instance, that the interpulse is maybe from a different location than the main pulse. So I asked Jim Cordes at the time, hey, did you have any interpulses here and do they correlate differently? But he didn't. He had only main pulses, and so he couldn't test it. So we thought, okay, this is already a few years ago. Let's do this ourselves. There are lots of data sets from the Crab. So we got one from Westerbork. Westerbork is nice because it's an array, and therefore you resolve out a lot of the radio emission from the Crab Nebula itself. And at that time, the scattering was a bit longer, and therefore our resolution was a little bit better. And that meant that when we measured the time scale, we got a bit of a smaller number. Now I probably should explain this graph first. So it is somewhat similar. The very top panel is going from 0 to the end, is somewhat similar to what Cordes had, that you have some maximum correlation when pulses are really close together, and then it drops off toward later things. But what I show here is also the correlation in frequency space of pulses. So what we did, we take pairs of pulses, we correlate them with each other, and then if all the pairs that are within 1 second, they form one column in this grayscale image. All the pulses which are a bit more separated form another column, etc., etc. And so for the main pulses, that is necessarily symmetric because the pairs, you can always treat them in the reverse way with the reverse time offset. But if you now compare interpulses with main pulses, and there are very few interpulses, so this is extremely noisy, you see that it doesn't look the same. Now, this was not a very high significant result, but what is significant is it's clearly wider. That means that the interpulse region almost certainly must be bigger in which these pulses occur. And it may be at the 1 sigma level is also slightly offset from 0, which we were very disappointed that we couldn't do much better than that. But it was clear that something is working, that we could tell that at least these two regions are not identical. Now, one thing that was very strange is that in contrast to Cordes et al., which had this maximum correlation of 1/3, we get a maximum correlation of only 3.5%. And we were very puzzled by that, and in the end, sort of, well, that actually held up the revision of the paper quite a bit. And in the end, we decided we understood what it was, but that came only from a next data set, which was analyzed by Rebecca Lin, and I should have mentioned her explicitly at the start. There were 2 students mentioned there, Rebecca Lin and Akanksha Bai, who really did most of the work here, and I'm presenting really their results. And so I'll start with Rebecca's here. So we were intrigued by this, and this Westerbork data was clearly just not good enough. So we got an even better data set from the European VLBI network. That means you resolve out the nebula even more. You get more pulses, therefore. It was really meant to make a parallax measurement, which we haven't done yet, and which Rebecca's working on now. But we just looked at the pulses themselves, and we made a similar kind of plot. So again, the sort of horizontal axis tells you how long pulses are correlated, the vertical axis how wide their frequency band is. And the top is main pulses with main pulses, and the bottom is main pulses with interpulses. And in some level, we find sort of into zeroth order the same thing, even though we have many more pulses and a better data set. It sort of looks quite similar. But really one thing has changed. There's actually quite a lot stronger scattering tail, which means we have a much better resolution. And one can sort of see that from the fact that the width in frequency has become narrower. Now, despite this higher resolution, the width in time has not become much shorter. And that actually immediately tells us something, that this width is no longer determined by how good our effective resolution from the scattering screen is, but rather by how big the emission region is. So if you imagine you have some quite small resolution element and something big is passing by it, it will basically, the duration that you'll get will be takes as long as how big that thing is that's moving by. So we measure actually the size of the emission region somewhat directly. And we find it's 850 kilometers, which is sort of pleasing. It's quite comparable to the light cylinder radius, and immediately tells us that indeed these pulses do not come from just right near the neutron star. Then it would be much smaller. There's no way. Now again, we find that the interpulse main pulse one is a little bit bigger. I think you can sort of convince yourself, hopefully, that that's true, and it must be a little bit bigger. But the reason that we're not doing much better is that our amplitude is yet lower. So where before we had 3%, now we have actually a 0.3 is not true, it's 0.5%. So it's much lower still. And the only way that can happen is that because our resolution elements are now so small that, that if you have one giant pulse going off and another giant pulse going off, most of the times they just, because the emission regions are quite large, they sort of go off somewhere and they're not close enough to each other to actually get much of a signal. And that is really strange. And then we thought, well, also what was strange is that we actually don't find any examples where one giant pulse is really well correlated with another giant pulse. And that suggests that these giant pulses are made up of pieces, that maybe those pieces are resolved themselves too. And so we in this paper, we tested that in a way that I will just, oh yeah, before I go, that I just to have some sort of sanity check that any of what I'm telling you is actually true, because I realized this is one of those things where we've now thought about this for a year or so. And here I am in 20 minutes trying to explain it all, and you have no intuition for it. I certainly didn't when I started this. But there's one way we could tell this, and that is by comparing the first and the second half so we took all the giant pulses and we correlated the first halves of pairs with each other and the second halves. Now, in principle, the second, I mean, there's lots of pulses going on in there, so it's a little bit messy, but in the first half, you cannot have had much scattering. So basically, right, so if I have my direct line of sight and I have my little delta, which is the maximum that the scattering does, then in the first half of a giant pulse, I can't have reached that yet. I can only have gone to a somewhat smaller delta. And that means that my effective resolution of that of my microscope with which I'm looking at these giant pulses is still poor, right? So if I just do the first half, this tau is smaller and therefore my resolution is bigger. And I can't resolve things so well. And you indeed see that therefore in the frequency direction, this is a lot wider because we basically don't have the same resolving power. So there's less things that are very close together in frequency will behave the same way, while near the end of the pulse, even things that are quite close in frequency, they now, right, there's such a large path length difference between the longer path and the shorter path that even those get out of phase. So it becomes much narrower. So this is really just to show that actually things do work. And now I wanted to look at, hey, how can we understand whether these pulses themselves are also resolved? So the individual nanoshots, that sort of felt that we were led there, and then we came up with a test for that, which just looks at the individual pulses and uses that we have measurements in both left and right polarization, and we can correlate those two. And now from a very long derivation, one can show what should happen, but it's really easier to just simulate it. So what we did is, what Rebecca did rather, is she takes, assumes each giant pulse is composed of either 2, 8, or 32 nanoshots, and they have sort of random polarization on the left here at least. And now if you assume that all these 32 nanoshots, they're all seen the same way through the same bit of the screen, then what you expect if you correlate the two pulses is that if the given giant total polarization is really high, you should get really good correlation, because basically the signals in the two polarizations are exactly identical. While if the polarization is really low, so that means the two signals in the polarization are really almost from different nanoshots, you should get back to this magic number of 1/3, which you get for pulses which have which go through the same screen, same impulse response function, exactly same paths for the nebula. And but on the other hand, if each nanoshot goes through a different screen, you get a completely different relation. You actually should go towards 0 then for the unpolarized giant pulses. Now, from my long derivation, I found if you take, instead of that, just the degree of polarization squared, you take the linear polarization squared divided by the intensity minus the circular polarization squared, that then you should get a straight line. If they all go through different screens. Well, if they all go through the same screen, you still go to a third, and it's sort of a mess. There's no analytic solution to it. Now, Rebecca also realized that if your shots are to start with all linearly polarized, which from higher frequency observation seems to sort of be the case, you also get a line in the one case, and in the other case, you still go towards 1/3. Now, reality is that it's much closer to that line in either of these two measurements. And so we learn from that the shots are probably randomly linearly polarized, and that we are indeed resolving these screens. Now that is really weird. And the reason it's weird is that we know these nanoshots, they come in the envelope of one giant pulse, so they're surely causally related. They're separated by maybe 1 microsecond. So that's about 300 meters of light travel time. So how can we resolve that if our resolution elements are maybe a few hundred kilometers? And that brings me to the second paper. Just check if I'm really not doing too well either. Okay, so I'll rush it a little through, where we had, that is a Kangsha's paper, where we had individual pulses from the Algonquin Observatory. And what you see here at high frequency, they're not so much scattered. At low frequency, they are scattered. And we had one really strange pulse, which had bending, and that is from interference between nanoshots. But the other thing that did these bands moved through the scattering tail. And that is bizarre, because in the scattering tail, all you're doing is looking at a very, very slightly different angle at the same neutron star. So how is that possible? And our picture is that what's happening is that we have a blob of plasma that moves a bit away from our line of sight, and we first get direct light to us, which comes at one velocity, and then as we get light a little bit scattered towards that direction the blob is moving, we get slightly blue shifted plasma, and so it slightly moves up over the scattering tail. Now, because this is such a crazy small angle, it's only less than an arc second, the only way you can get this to work is if this is moving really highly relativistically with about a gamma of 10,000. Now, just very quickly, this sort of works. We can make a simple model where we say, okay, we take the initial spectrum, let's just shift it and decay it, and that's great, that works. And now it is interesting that if it moves so fast, then it will lead to apparent superluminal motion on the sky. So if you're looking at it from the side, you think that things come only very quickly after each other, but in reality, a lot of time in your in the neutron star frame has happened, and things shift on it, and you can calculate, and then you find actually that for a few microsecond duration for the angle that would be relevant at 1.5 gigahertz, where Rebecca's observations were, the transverse size is about 1,000 kilometers, which we could easily resolve. So that gets me to my conclusions. We've used the nebula as a microscope. We resolve the two interpulse emission regions. We find this amazing, highly relativistic motion. I think this is the first true measurement of anything moving that fast. Of course, I'm sure that there's something alternatives could be found if needed. This has implications. It means the energetics are in some sense easier. Things are not really as bright as they look. It's mostly boosted from relativistic motion. If the same is true for FRBs, that means their energy budget is much reduced. And it's actually quite consistent with a nice theoretical work by Maxim Lutikov, a former citizen, about how this emission should occur. So I better stop. Thank you.
Thanks, Martin. Hey, we're out of time, but maybe is there a quick question? It's a really very cool result. So if there's a quick question, put your hands up right away. I guess we better just get on with our days then. Hey,
Okay,
thank you so much, Martin. That was awesome. You're basically measuring the index of refraction of the Crab Nebula. That's so cool. Okay, so thanks everybody, and we're looking forward to seeing you in a week's time for our next talk. Bye.
Thank you.